What's going on, guys? Johnny Bannon here with Trepa Technologies, and in this video we're going to be going over wireless security. This is a video in our entire series of videos of our free CCNA course on YouTube. If you're interested in our paid course with over 1,200 practice questions, access to our Discord, labs, and one-on-one training with your instructors, please check that link in the description below if you want those resources. If not, let's go ahead and jump right into it. So in this video, we're going to be covering everything wireless security. Now, this is going to be at the CCNA level. So if we actually look at the CCNA exam objectives, they just want us to be able to describe WPA, WPA2, WPA3. Then also configure WPA and WPA2 pre-shared key and on a wireless LAN controller GUI. So in the GUI, they want you to know how to pretty much click enable for the WPA and WPA2. This slide deck that I made is about, I think, 26 slides. It gets pretty in-depth. Now, in your CCNA studies, a lot of things we're going to go over, you may not see on the exam. Now, I don't know what's on the CCNA exam, but if their CCNA exam objectives are accurate, then yeah, we go pretty in-depth, probably a little bit more than what's needed. With that being said, it's good fundamental knowledge. As I always tell my students, yes, we're here to pass an exam, but we're also here to learn. And as you get these fundamentals now, it'll help you further along in your career when you go to different enterprises, when you work on different networks and you say, hey, I remember learning about this. Let me now look into it. So it's good that we are going in depth on some of this wireless security. So to start off, we're going to just go over, kind of recap from our other security essential videos, authentication, encryption, and integrity. And then we're going to get into the different authentication methods, then the different encryption and integrity methods we use in a wireless LAN or a wireless network. So with that being said, let's go ahead and get started. So let me move my face out of the way here. And then let me go back to the beginning. All right, so on the agenda today is going to be wireless security fundamentals. Of course, we're going to go over authentication, encryption, and integrity again. And then we're going to go over the different authentication protocols. So I only have 3 listed here: Open Authentication, WEP, and then EAP. This will make more sense because EAP is actually just a framework that you can build on top of. So there's a lot of different extensible authentication frameworks and protocols that we're going to learn about. And then we have different cryptography protocols. So that is going to be TKIP, AES, CCNP, GCNP, the different ways that we actually apply cryptography and encryption on our wireless LAN and our data and our 802.11 frames. We're also going to talk about mix and integrity checks as well. And then we're going to go over the different WPA standards and the different modes and methods in which we deploy them. So what encryption does WPA use? What kind of modes does it have? And how do we deploy it? Okay, so the wireless local area networks use Wi-Fi or RF signals to connect Wi-Fi enabled devices to the switched or the backbone network. Now, because these signals are broadcasted, there is not inherent protection like there would be in a wired network. So what do we mean by that? Well, when we have a LAN, typically from our LAN users to our switches to our router to our local servers, we won't have data in transit encryption. It's not really needed, right? We only do that when we're going across the internet, maybe to a foreign web server out on the internet on our untrusted networks. So we do TLS, right, for HTTPS requests. Now in the LAN, we typically won't do that. We'll have authentication, of course, but proper encryption, not really. That's because when we plug in Cat5, hopefully no one's doing a wiretap on us, stealing the bits and then re-encapsulating them to see what's going on in our LAN. If that's happening, there's a bigger problem because you have insider threats and a physical security problem that technical implications won't change. Why is that different than Wi-Fi and wireless networks? Because without encryption, without authentication, our SSIDs and our wireless LANs are being broadcasted. And anybody with an antenna that can receive Wi-Fi signals within their frequency range, 2.4 gigahertz, 5 gigahertz, and the channels, the proper channels, they can receive the traffic and can listen in on all the data being sent back and forth between client and access points. So since they're openly broadcasted, we need to protect, encrypt, and authenticate this traffic within our LANs. So typically, again, in a wired network, we only encrypt our traffic crossing like the internet. So the three main concepts we're going to cover for protecting our Wi-Fi networks are how we authenticate, how we encrypt, and how we provide integrity. Okay, so wireless security authentication. So Wi-Fi enabled clients must be authenticated before they can associate to a wireless access point. So before this computer, this Wi-Fi enabled client starts sending data frames to this access point, it needs to be authenticated. So what that means is it's going to go through an association process to that BSS, to that SSID, or to that wireless LAN. So in your enterprise, what you're typically going to see, just a very basic network, right? Like a CCNA certified individual would see, is you'll have like a corporate network, your business network, and then a guest network. And then the corporate network will have its own SSID separate from the guest network. There'll be two separate wireless LANs. Now, why is it important that not only does this access point authenticate us, why is it important that we also authenticate the wireless access point? Because there could be malicious APs out there, sometimes known as evil twins, that could be mimicking that corporate network or your good SSID and network, and you don't want to connect to them. So it's important that we understand that the authentication process goes both ways. And there are multiple ways to authenticate. So we have, and what I mean by that is when we authenticate from our Wi-Fi enabled devices to the access point, we can use a password to authenticate. We can have credentials. So we can have a username and password. And you're going to learn about that with 802.1x, Radius, and Enterprise mode. Don't worry. And then we could also have even digital certificates. So we could have an environment where we have local certificate authorities, certificates. Sometimes I'm really bad at spelling, guys, when I'm being recorded like this. Digital certificates. There we go. So sometimes you could have it where your enterprise wireless LAN could be doing LDAP syncs, and you could be using like tokens, like in the government we use CAC, common access cards, that have digital certificates on them to authenticate to a wireless network. Okay, and then encryption. So once authenticated, now that we know that we're on the right SSID and the user has now authenticated, and now we're sending 802.11 data frames, now what do we need to do? Because remember, this traffic is still coming over the air. It's still being broadcasted on those Wi-Fi signals. Now we need to encrypt from Wi-Fi client to the wireless access point. So we have what's called confidentiality between the client and wireless access point. So all devices within the same wireless LAN will use the same type of encryption. However, each client to WAP connection will have unique keys. And what we mean by that is if we're using private keys or public-private key pairs, they're going to be unique between client and wireless access point. Sometimes it will, if the wireless access point needs to encrypt traffic, it will use a group key to send to all its clients at the same time. And there's many possible protocols that are used to encrypt the traffic, and we're going to get into that. With the Wi-Fi protected access standards, we have WPA through WPA3, and each one has their own different flavors of encryption, and some are even antiquated, right? Some are even vulnerable. So we're going to get into that. But just to get a brief preview, WPA uses TKIP, WPA2 uses CCNP with AES, and then WPA3 uses GCMP also with AES, okay? So we're going to learn deeper about those encryption methods later on in the section. Now, let's go over integrity. How do we ensure integrity on our wireless LANs? So what is it, first off? What is integrity? So integrity ensures that data in transit or a message in transit has not been altered or changed. So if you're watching these series of videos in order, when we go over hashing, we talk about how hashing isn't encrypting. It's just verifying that data that you've downloaded or a file you've downloaded hasn't been changed from the website you downloaded it from that transit to your computer. So how does wireless networks verify integrity? They use something called a MIC, a message integrity check. That is added to the 802.11 frames/messages to help protect their integrity. So let's go over the steps. So the sender, let's say we have a client here. We have a computer. What will happen when they're sending their 802.11 frames is the sender will calculate and make using a hashing algorithm like HMAC SHA-256, and then it appends that MIC to the data frame, typically in the FCS field. So we kind of see my diagram here. So here's that original message, and this is an 802.11 data frame, and we're going to append a MIC. And then here's that MIC value, okay? Try to make a little hash. And then the sender is going to encrypt that data frame and the MIC. So it's encrypting the data payload, the frame, the 802.11 frame header, and the MIC along with it. And then using an encryption algorithm, and let's just say, for example, like CCNP with AES, they're going to encrypt that entire message. Once the wireless access point receives that, it's going to decrypt the message, and then it's going to extract the MIC. It's going to say, okay, there's the MIC value. Then it's going to do recalculation. So now that it has that original value here, the receiver, the wireless access point, is going to recalculate the MIC from the received data frame using the same cryptographic hash function and the shared secret key. So if we used HMAC SHA-256 as the sender, that's what the receiver will use to recalculate the MIC, the message integrity check. And then it's going to compare it and accept it. So if the receiver's calculated MIC is equal to the original MIC from the sender, it's good to go. And now we know that data has not been altered. And now we can accept it. And now we can pass on that data, okay? So that's just a basic overview of the steps used in wireless security integrity. Now let's get into these different authentication modes. So there is a lot on here. So let's just go over this real quick, guys. These authentication modes, really there's just three main ones, and you'll see what I mean by that. There's open authentication, and then there's the first authentication method, WEP, wired equivalent privacy. So you can kind of see when they made that up, I think in 2002 or 99, can't remember now, but they were saying, hey, this is just as secure as your copper lines, and turned out that wasn't the case. And then we have EAP, the Extensible Authentication Protocol. This is the framework that builds all these other EAP authentication methods that you see here. So yes, you have 7 on the screen right here, but really we're going to learn about these two, and then we're going to learn how this is a framework, and then learn the different ins and outs of all these different extensible authentication protocols, because they're all different. Some are already vulnerable, and some are more secure than others, and each have their different ways to provide authentication in a wireless LAN for enterprise mode, okay? So the default, authentication or open authentication. So the default access method here is the open system authentication, and it's the simplest method used in wireless network. It allows any device to attempt to connect to the wireless network without needing to provide any credentials up front. So really under this, there is no authentication, right? All we're doing is just sending a request and then an association and getting responses for that. So there is no security. So open authentication, the only security that it provides is just verifying that the device is Wi-Fi capable, right? That's all it does. Typically, if you see this used actually, it's going to be in public hotspots. So imagine when you go to Starbucks, so you go to a hotel and you connect to their network. It's completely open, right? And you get online. And then what's the first thing that happens when you go on like Google Chrome or your web browser? A captive portal comes up that says, hey, now put in that Wi-Fi key, or now put in your username and password or your hotel room and last name, right? So that's how you can kind of make open authentication secure. But it's not. There is no authentication in it at all. The only authentication it does is just, again, the actual management frames, the management 802.11 frames. Just send this. They're just like, hey, are you the SSID? Cool, let me associate. Awesome. And that's it, guys. That is open authentication. The authentication method that came right after that was WEP. So this is a legacy encryption standard. The wired equivalent privacy WEP was one of the earliest encryption standards used in wireless networks. It was designed to provide two things. One, of course, authentication, and then also confidentiality. So WEP is also an encryption method, okay? It's also an encryption method, but right now we're talking about how it provides authentication, okay? So the way it does it is WEP uses a shared key authentication method where both the wireless access point and the client device share a common secret key. This key is going to be used to authenticate and then encrypt and decrypt data. So with WEP, it relies on manual configuration of shared keys on both the access point and client devices. This can be challenging to manage in large networks and lacks the scalability of more modern security protocols. So while WEP attempts to provide data integrity, guys, through something called a CRC, which is a cyclic redundancy check, it is not effective in preventing all forms of data tampering or unauthorized access. So we don't really recommend WEP. It's vulnerable, right? And if we actually look at this shared keyed authentication here, so we have our authentication response from the client, which is nothing. It's clear text. Then the authentication response is sent with clear text, and it's a challenge that's sent back to the wireless the wireless client here. And then we do another authentication request with the WEP encrypted challenge. So now we're encrypting, and then we send back that authentication response. And then if it's successful, now we can associate to the network. So WEP encryption. Now I know we're getting a little bit ahead of ourselves, right? We're going over encryption during our authentication methods, but that's okay. It all ties together. So the wired equivalent privacy provides encryption in wireless networks through the use of a simple encryption algorithm known as the RC4 stream cipher. Now in the CCNA, it doesn't say we need to understand the RC4 stream cipher. If you want to learn more, we talk about it in our Security Plus or go on Wikipedia. It's one of the earliest stream cipher algorithms and encryption standards, so there's a lot of information about it. All right, moving on. So WEP. WEP relies on a shared secret key, which is typically entered manually into both the wireless access point and the client device, meaning like a password that you would type in from your client. This shared key is used to generate two important components. One is the initialization vector and the actual WEP encryption key. So the initialization vector, this is a 24-bit value that is combined with the shared key to create the actual encryption key. The IV's purpose is to introduce variety or variability into the encryption process, ensuring that the same encryption key is not used for every data packet. So again, if you haven't been through a cybersecurity course, this may sound like foreign to you. But what we're talking about here is this stream cipher RC4 that's being used. It's being used with an initialization vector, or that WEP encryption key, okay? So WEP by default uses a 40-bit and a 104-bit key, encryption key. When we add that IV in here, every time, let's say we want to encrypt this packet of 1500 bytes, right? We'll use that same 40-bit encryption key. Well, what's going to end up happening if you keep doing that over and over to traffic? Someone will eventually, if they're doing like sniffing, will learn the pattern and learn how to decrypt it because you're using the same encryption key each time. So what this initialization vector does is it takes up space here and then adds, what I mean takes up space is usually keys come in like 64, 128. So WEP should be a 64-bit key, but it takes 24 away to do an IV, which adds on additional variety or variability into the encryption process so that the same key that's being used, it's a different encryption every single time, okay? So that's how an IV works. And if you take like a Security Plus course, we go over that and cover how that makes stream ciphers better protected, okay? So technically, yes, WEP is a 40-bit and 104-bit key size, but when you add in that IV, and depending on how you look at it, it's either 64 bits total minus the 24-bit IV. No matter how you spin it, it's 64 bits and 128 at the end of the day. But depending on what exam you might be taking, they could say that WEP keys are actually 40-bit and 104-bit technically. Just depends. Now, with the data encryption. So when a client device wants to send data to the access point or vice versa, it takes the plain text data, combines it with the IV to create a unique encryption key for that specific data packet. And then this encryption key is used with the RC4 stream cipher to encrypt that data. And then that encrypted data, along with the IV and also a CRC, a cyclic redundancy check, are placed into that data frame for transmission over the wireless network. The frame header also includes the IV for the recipient to know which encryption key to use for decryption. So of course, if our client is attaching an IV to a header and then using that to create an encryption key, a unique encryption key for every single data packet, the receiver, there's my wireless access point receiver, also has to know about that initialization vector, okay? So that is in a nutshell how web encryption works. Now, let's move on to extensible authentication protocol. And we're coming up on like our 20-minute time frame here, so I'll probably just go over this slide and then move on to the next slides in the next video, okay? So the extensible authentication protocol, this is an authentication framework, meaning it's not a single method. It's a framework for various authentication methods within the wireless network. So it's something for us to build off of. So it provides flexibility in choosing authentication mechanisms tailored to specific security needs. So there is diverse authentication methods when using EAP. So what we mean by that is, let's think about our hardware, right? So if we're building a wireless access point and a wireless LAN controller, we just have to be able to use EAP, and then we get all the different authentication methods that get built on top of it, okay? So EAP is just a framework we can build off of. So EAP encompasses a wide range of authentication methods like EAP TLS, which is one of the more secure ones, EAP PEEP, or protected EAP. We also have tunnel transport layer security, which I don't think we're going to touch on, but it's just one of the more modern examples and secure ones. What it also provides is that client-server authentication. So in wireless networks, EAP typically operates between the client device, an authenticator, and authentication server. So it works in conjunction with something called 802.1x, which is a part of our network access control, and it's port-based. So what are we talking about here? Let's take a step back, because we were just saying it's its own framework. Yes, but it works in conjunction with something called 802.1x, which if you go look at that RFC standard, it is a technology that provides us port-based network access control and uses a AAA protocol like Radius to provide authentication, okay? Now let's get into how 802.1x works, okay? So the way 802.1x works is it's going to have three main components, and this is used to limit network access to clients on a LAN or wireless LAN. And we're going to have three things that we talk about here. So one is the supplicant. The supplicant, which is our device right here, this is a device that wants to connect to the network. So our supplicant here is saying, hey, I need access to the wireless LAN. Then the authenticator is the device that provides access to the network. So in a case of wireless LANs, that would be the access point. And in a split MAC architecture, or if this is like a lightweight access point that has cap-wap tunnels to that wireless LAN controller, it's actually going to be this wireless LAN controller that is the authenticator. So that authenticator provides that device access to the network. And yes, we're connecting to an access point, but if you remember from our wireless section, there's a data and control cap-wap tunnels that send all traffic to the wireless LAN controller if you're in a split MAC or lightweight deployment. Okay, and then we have the actual authentication server. So this is a device that receives the client credentials and permits or denies access. So with this is typically going to be used in something called enterprise mode. And that's because this Radius server here, this AAA server, is either going to have an LDAP sync back to your ADUC environment, or you're going to have actual credentials created on the Radius server itself or AAA server itself. So we have to use enterprise mode here. So when you connect off to this wireless access point, you get access to the wireless LAN, you should be providing a username and password. So that is how EAP provides us an extensible framework for authentication, right? It is in conjunction with this 802.1x method. And now this process here of sending this information, there's going to be a bunch of different ways we can encrypt and provide integrity to this whole authentication process. And that is where we have these different EAP frameworks here with protected, with TLS, with EAP fast that we're going to go over, which is vulnerable now. But we got to learn about it so we understand how these frameworks work in the context of authentication and how we protect our authentication process with encryption and integrity. All right, so that's going to be it for this section. We'll call this part 1 of our wireless security section. So again, remember, it goes deep, and our next part is going to go pretty deep as well, because we're going to have, like, I don't know, maybe 10, 12 more slides to cover. So stay tuned for our part 2, where we go into the actual other EAP authentication frameworks. And if you like this video and you like our training, and you're an active duty, reserve, or National Guard soldier, click that link in the bio, because you're entitled to $4,000 a year in free certification and credential assistance, where you could use your credentialing assistance to come to our live or our self-paced CCNA course, which has over 1,200 questions, live instruction, bonus content labs, access to our Discord, and one-on-one with our instructors that can help you get job placement, help you with resume building, especially if you're an ETSing or transitioning soldier. So stay tuned for our video, our part 2, and don't forget to like and subscribe.